In this file, we show how to use the hammer and sauto tactics in a formalization of the greatest common divisor function. A number d is a common divisor of a and b if a modulo d and b modulo d are both 0. A number d is the greatest common divisor of a and b if it is a common divisor of a and b, and for every d prime, which is a common divisor of a and b, d prime is less or equal to d. Here is a helper lemma we need in the formalization of the greatest common divisor function. It says that if b is not 0, and d is the greatest common divisor of b and a modulo b, then d is the greatest common divisor of a and b. I won't be explaining the proof of this lemma in detail. Here the hammer tactic helps us with some easy subgoals which require lemmas from the standard library. The hammer tactic is useful in a scenario when the user is not very familiar with the library, doesn't know which lemma to use, and can't find the lemma easily using CoqHammer search command. Here, finding the necessary lemmas with the search command is doable, but it takes a bit more time than using hammer. Here we see hammer can find the necessary lemmas quite quickly. And this seems to be faster than using the search command of Coq. Well, here it took a bit more time, but still it was relatively quick. Here the ATPs succeed, but hammer cannot reconstruct the proof. We still get some useful information from the hammer tactic though. The necessary dependencies found by the ATPs. We then, after proof reconstruction fails, we prove the goal manually using the lemmas returned by the ATPs. The annoying thing about proof general is that once the hammer tactic fails, the previous messages disappear here from the response buffer, but we can always see them in the Coq buffer. We see everything that Coq printed before, and we see here the dependencies. Here it is also displayed which hypotheses are necessary to prove the goal. This means that any other hypotheses were not used by the ATP, except HB and HD. So we clear all other hypotheses. Here in the comment, I've written the lemmas returned by the ATP. And indeed, it is possible to prove the goal with them, but somehow the reconstruction tactics could not find the proof. Finally, we implement the greatest common divisor function. The result type here says that the GCD function returns a number d, such that if at least one of the arguments is non-zero, which is equivalent to saying that their sum is greater than 0, if this holds, then d is the greatest common divisor of the arguments. The function is not structurally recursive, but the second argument decreases in the recursive call. We are left with some obligations to prove. In the first obligation, we use the S-intuition simplification tactic, which here just splits the goal, and we're left with 3 sub-goals. We try hammer in the first sub-goal. It succeeded relatively quickly, the unfold option in the reconstruction tactic turns out to be actually unnecessary. In the second sub-goal, we also try hammer. This goal can actually be proven by S-auto without using any lemmas from the library. But the S-auto tactic takes over 0.3 seconds here. Before doing premise selection and invoking external ATPs, the hammer tactic tries to run S-auto for 1 second. And if S-auto succeeds, it forgoes the 3 phases and prints S-auto as the reconstruction tactic. The time limit for the initial run of S-auto can be controlled by the set hammer S-auto limit command. Setting the limit to 0 disables the initial run of S-auto. Now hammer invokes the external ATPs. It succeeded. Actually, only one of the lemmas is needed to prove the goal with first order. And this is the first NAT mod 0L lemma, which we can figure out by just trying to delete the lemmas here in the use option and see if it still works. The gain here is that with the NAT mod 0L lemma, first order can prove the goal much more quickly than S-auto without any options. S-auto is strong enough to prove the goal without the helper lemma, but then it takes noticeably longer. The third sub-goal. We run hammer. It works. The reconstruction tactic now takes a while in this case, but it works. The next obligation. Hammer works here, it finds the necessary lemma. The third, final obligation. Here we have the first projection in the goal. As mentioned before, hammer's effectiveness is very poor outside the first order fragment of Coq. So we need to remove this first projection from the goal to have some hope of success with the hammer tactic. We do this with the simple sigma tactic from the tactics module. Now we run hammer. The CVC4 prover succeeded, but somehow the S-auto based reconstruction tactics couldn't recreate the proof. Actually, we only need our helper lemma here, and the sub-goals may be solved using LIA. We have thus defined a fully specified formalized greatest common divisor function. We can compute with it